All right, guys, so in this second acid-base video, we are going to be learning about conjugate pairs. So every acid or proton donor produces something that would then be capable of being a proton acceptor. So after your acid loses its proton, it becomes a proton acceptor. And when you have something that gains a proton, it now has a proton that it could donate. So acids turn into bases and bases turn into acids, and these are going to be called conjugate pairs. So we're going to be learning about that today, and we're also going to learn about what it is that determines the strength of an acid. So we may know that something like, oh, hydrochloric acid is scary and strong. So why is that? Why is hydrochloric acid strong? And something else like, say, acetic acid, which is in vinegar, or citric acid, which is in lemon juice, not a strong acid, what we consider a weak acid. So it's going to turn out that strong acids and weak acids, what makes it strong and what makes it weak is actually the base component. So what we're going to be learning today is that it's really all about that base. The first thing we're going to be talking about today is conjugate pairs. In order to look at conjugate pairs, we're going to write a sort of generic version of an acid reaction with water. So we have our weak acid, HA, where A just stands for the rest of the acid, and H is the proton that can get lost, reacting with water. And when you put an acid in water, the proton comes off and we make H3O plus and A minus. HA is the proton donor in this reaction, and H2O serves as the proton acceptor in this reaction. After the proton has been donated to water, we are left with A minus. A minus is called the acid anion. It's the anion that's left after the proton has been lost. An acid ion is something that's capable of being a proton acceptor. Since A minus could accept a proton, it technically is now a base. And so what we've just seen happen is we've seen our acid turn into a base. We can also look at what happens when the H2O has accepted its proton. So after accepting the proton, we have H3O plus, which is capable of being an H plus donor. So our proton acceptor has turned into an acid. So we have an acid that turns into a base, and we have a base that turns into an acid. Because the A minus, the acid anion, came from an acid, we call it a conjugate base. Conjugate base, where the term conjugate refers to the fact that it was an acid and after it lost its proton it became a base. H3O plus then is a conjugate acid, something that started as a base and turned into an acid after accepting a proton. What we now have here are two conjugate pairs. The HA and A minus are one conjugate pair, And the H2O and H3O plus are another conjugate pair. The conjugate pairs always consist of an acid and a base. So we cannot have an acid-base reaction without generating a conjugate acid and a conjugate base. These things always come together as a pair. So acid-base pairs, like the ones we established above, are conjugate pairs. They consist of HA and A minus, or H2O and H3O plus in the case of our reaction above. What this really means is it consists of an acid and conjugate base, or a base and a conjugate acid. Let's look at some examples and have you practice this concept a little bit. Let's see what happens if we react NH3 and water. So NH3 and water, we make NH4 plus and OH minus. Pause this video and see if you can identify the acid, base, conjugate acid, and conjugate base. Okay, let's see how you did. In this reaction, acid is water. Water is acting as the acid. It's the thing that donates a proton to the ammonia. So ammonia is the base, and the conjugate acid that forms is the ammonium NH4 plus ion, and the conjugate base is the OH minus ion. Do you want to try one more? Let's do HF. HF and water will make H3O plus and F minus. Pause again and see if you can identify the acid, base, and conjugate acid and conjugate base. Okay, do you think you have it? HF should be the acid, F minus should be its conjugate base. H3O plus should be the conjugate acid to H2O being the base. So in these examples, the pairs HF and F are a conjugate pair. H2O and H3O plus are a conjugate pair. In the ammonia example, ammonia the base and NH4 are the conjugate pair. Water and OH minus are the conjugate pair. The pair is always a base and a conjugate acid, and an acid and a conjugate base. You can't have a base and a conjugate base as a pair. Now that we've talked about conjugate pairs, we can start the topic of acid strength. So there are strong acids and weak acids, and there are weaker weak acids and stronger weak acids. We're going to be exploring what makes something a strong acid or a weak acid. To do this, we are going to use the generic equation for an acid reacting with water. And it makes H3O plus and the acid ion A minus. So this chemical reaction is what we're going to be focused on, and we can think of this as an equilibrium reaction, right? Because HA and H2O, this is an acid, this is a base, but it makes a conjugate acid and a conjugate base. We have a base and an acid, so this could accept a proton and go back in this direction. This is feasibly a reversible reaction. And so because it's a reversible reaction, we can have an equilibrium expression for this particular reaction. It would be the concentration of the products, which are H3O plus and A minus, over the concentration of the reactants, except that water is a pure liquid. So it won't be part of the equilibrium expression. Only the weak acid will be part of the equilibrium expression. So we call HA undissociated acid, which means that it hasn't broken up, it's staying together. The H remains bound to the acid anion. On this side, we have dissociated acid, where the H plus, the proton, has come off of the acid anion. This particular equilibrium constant is called a Ka. A Ka is simply a Kc expression for an acid losing its proton. So the A just specifies that it's for an acid, just like the W and Kw specified it was the reaction for water. So we can think about this from an equilibrium standpoint. Ka values can be big or small. A big Ka value, just like a big Kc value, will favor the products. What that means is that there's going to be more H3O plus, less undissociated HA. If the H3O plus concentration is higher, then it's going to be more acidic. We saw this when we learned about pH. Higher H3O plus concentration is going to equal a lower pH, and it's going to mean it's more acidic. So a big Ka leads to a more acidic solution. A small Ka is going to favor the reactants. That's going to mean that there's more HA and less H3O plus. That's going to lead to a lower H3O plus concentration, and that's going to mean a higher pH and a less acidic solution. So a big Ka gives us a stronger acid, and a small Ka gives us a weaker acid. We generally break acids down into two categories: strong acids and weak acids. Strong acids are considered any acids that fully dissociate. These are ones that don't form an equilibrium. They are irreversible reactions. So strong acids fully dissociate, they are not reversible, and they have no equilibrium. A weak acid only partially dissociates. These are reversible reactions, and they do form an equilibrium. We don't really talk about Ka values for strong acids because they're not reversible. For weak acids, though, a higher Ka is going to be associated with a stronger weak acid, and a lower Ka will be associated with a weaker weak acid. So strong acids, you need to learn to recognize a few of these. HCl, HNO3, nitric acid, H2SO4, sulfuric acid. These three acids you absolutely need to know are strong acids. The other two that you should probably know are HBr and HI. These are also strong acids. You can pretty much assume almost everything else that you encounter is going to be a weak acid. There's a couple extra strong acids, but I don't want this list to be overwhelming for you. So if you learn these 5 acids are strong acids, then you can assume everything else is a weak acid, partially dissociates, and establishes an equilibrium. So if we come back up here to the top and think about this equilibrium reaction, what we've established down here that there are strong and weak acids. So what is it that's going to make some of these equilibrium reactions and some of them go only one way? Because that's ultimately what's going to determine acid strength. We might think it has something to do with the acid, the hydrogen, the HA, but it actually doesn't. It has everything to do with the base, A-. So acid strength is all about the strength of the conjugate base. The acid anion determines the acid strength. And that's what we're going to explore on the next page. Okay, so we have this reaction. HA plus water makes H3O plus A-. I'm just rewriting it so we have it on this page. What we're thinking about is what would make the reaction want to go back this way versus stay in the forward direction. So for a strong acid, the reaction is going to stay in the forward direction. For a weak acid, the reaction is going to go back towards the products, backwards. So what's going to drive this reaction backwards is actually the ability of A- to act as a base. If A- is a strong if A- is the conjugate base, right? So A- is the conjugate base. We're going to call it the acid anion, but it's also a conjugate base. And a base is a proton acceptor. I've always kind of been amused by the term proton acceptor. The reality is that bases are actually more proton takers. They want that proton, they take that proton. I like to think of strong conjugate bases like the Thors of conjugate bases. If you've ever seen the Avengers movie where he comes in and he's like talking to that huge rock man, he's like, I accept your surrender. Like he's really accepting his surrender. He's taking his surrender. So a conjugate base is a strong conjugate base accepts protons the same way Thor accepts surrenders. So we can say strong conjugate bases accept protons like Thor accepts surrenders. They take them. They don't accept them. And so what that means is that the reaction is going to get driven backwards. We're not going to have very much free A-. It's going to take the proton from water and stay as HA because that conjugate base is a pretty strong base. Weak conjugate base is a little bit more like this guy. Probably you can imagine they'd be like, oh, what, you want my proton? Here, take it. I'm not going to fight you for it. So if we have a strong conjugate base, we end up with a weak acid. Something that does not release very much proton into water. And when we have a weak conjugate base, we end up with a strong acid because the protons are easily released into water. Now that we know there's a difference between strong acids and weak acids, strong acids being acids that fully dissociate and weak acids being those that establish equilibrium and partially dissociate, we're going to explore the difference between how we would calculate pH for strong acid solutions versus weak acid solutions. So for strong acids, calculating pH is really simple. pH calculations are simple for strong acids. The reason it's simple is that the acid fully dissociates. Because of that, the H3O plus concentration in solution will simply be equal to whatever the initial acid concentration is, or whatever the HA concentration is. So all we have to do is plug this H3O plus concentration into our equation. pH equals negative log of H3O plus. You should pause this video here and go to the worksheet on Canvas, and you should try number 2A and number 2C to practice using this equation and calculating the pH for a strong acid solution. The answer to number 2A ends up being 1.2, and the answer to 2C ends up being negative 0.51. Yes, you can have negative pHs. It just means that it's a very concentrated acid. It's very acidic. An answer key will be posted on Canvas for this, so if you weren't able to get these answers, please look at the answer key and see if you can figure out what you did wrong. If not, contact me and we'll go through it. For weak acids, this calculation is more complicated. The pH calculations for a weak acid are going to require a rice table because we're dealing with equilibrium reactions. The HA does not fully dissociate. So in order to determine the H3O plus concentration, we have to go through the rice table process. We need the rice table process to determine the H3O plus concentration, which we need to find pH. So ultimately, in either of these, a strong acid or a weak acid, we are relying on this equation. In a strong acid, we can get that H3O plus concentration easily. In a weak acid, it's more complicated. We need to use the Ka and the rice table to figure out it. This is a good time for me to introduce something called the approximation method. Approximation method. You can do this with a lot of equilibrium problems, but it's particularly common for weak acid and weak bases equilibrium. So the approximation method tells us if the ratio of the concentration of the strong acid, HA, to the Ka value is greater than 100, then the value HA concentration minus X is approximately the same thing as just the HA concentration. What this range, if the HA over the Ka is greater than 100, then that means X, the change, will be very small. compared to, compared to the original concentration of HA. And so if you have hated significant figures for every reason all semester, you finally have a reason to be glad for significant figures. What we're going to see here in this scenario is that the change is so small that when we subtract it from the original concentration and then apply significant figure rules, the original concentration doesn't even change. So this allows us to really simplify the math in a Rice table. The best way to do this is to do an example. So we're going to work through number 3 on your worksheet together. So we're going to look at worksheet number 3 and use the approximation method and look at how we calculate the pH for a weak acid. In this example problem, we're going to calculate the pH of a 0.75 molar solution of citric acid. And the Ka for citric acid is 8.4 times 10 to the minus 4th. Kas are values that you can look up or are in your textbook or will be given to you in a problem. Ka is not something you need to memorize or know. All right, so citric acid is a weak acid. And that's really all we need to know about it. We don't need to know the structure to do this problem. We can just consider it a weak acid, HA. And so the reaction when we put it in water will be to form H3O plus and A minus. We can build our Rice table around this reaction. And I'm going to go ahead and cross out the water column because water is a pure liquid, so it doesn't participate in the equilibrium. So we can just cross it out and ignore it. We take the concentration that's given to us and we assume that this is the initial HA concentration. So our 0.75 molar will be here, and then we assume we start with no or zero dissociated. So when we're doing these problems, we always assume that it all starts together and it's not dissociated yet. All right, when it dissociates, we are going to form H3O plus and A minus and use HA, so that will be negative. So our equilibrium will be 0.75 minus X, X, and X. Now we can pair this with the equilibrium expression, which is H3O plus times A minus over HA. And plug in. So we have 8.4 times 10 to the minus 4th equals X times X over 0.75 minus X. So I am just plugging in these equilibrium values into the equilibrium expression. Once you get here, this is when you want to stop and check for the approximation method. So to check and see if we can use the approximation method, we're going to divide the concentration, which is that 0.75 over the Ka, which is 8.4 times 10 to the minus 4th. And we want to know, is this greater than 100? So we plug this into our calculator. This is approximately 900. So yes, it's greater than 100. Yes, we can approximate. So what does that mean? What do we do when we approximate? When we approximate, we're going to say that 0.75 minus X is pretty much the same thing as 0.75. And that substitution is going to go in right here. So now our equation simplifies to 8.4 times 10 to the minus fourth equals x times x over 0.75. What this is going to mean is that we aren't going to need to use the quadratic equation to solve this. This tremendously simplifies the algebra. So we multiply both sides by 0.75. That's going to give me 6.3 times 10 to the minus fourth on this side. X times x would simply be x squared. We can take the square root of both sides, and that's going to give me x is equal to 0.025. So now we plug this into our race table. And what that tells us is that the H3O plus concentration at equilibrium is X, which is 0.025 molar. So now we have the H3O plus concentration. We just plug that into negative log of the H3O plus concentration. And that's going to give us a value of 1.6 for the pH. If you'd like some additional practice, try this problem. What is the pH of a 0.100 molar solution of HCN? And the Ka of HCN is 6.2 times 10 to the minus 10th. The answer to this problem is 5.1. I'm going to post the answer key on Canvas so you can check your work and see how you did. You can also do worksheet number 5, problem number 5 on the in-class worksheet for one more round of practice. Again, the answer key is posted. I am almost done with this second acid-base lecture. I just have one more thing I want to introduce to you, and that's the concept of pKa. pKa is a simplification of Ka. So just like pH is a simplification of H3O plus concentration, pKa allows us to talk about Ka values without having to deal with scientific notation. And so whenever we can simplify something from like 8.4 times, oh, I did not spell scientific notation right there. Okay. Scientific notation. Right, so if we can avoid having to say something like 8.4 times 10 to the minus fourth and can instead say like 3.6, that's a lot easier. Same with pH. It's a lot easier to say the pH is 1.5 than it is to say the H3O plus concentration is, 1 times 10 to the negative third or something like that. So pKa and pH are ways of simplifying the numbers so it makes them easier to talk about. The equation is pKa equals the negative log of the Ka. What ends up happening math-wise here is that a smaller Ka equals a bigger pKa, and a bigger Ka equals a smaller pKa. And so a big pKa corresponds to a weak acid, and a small pKa corresponds to a strong acid. This is just like how a low pH corresponds to a high H3O plus concentration. You can practice this. Here's a couple acids. So HF, H2CO3, H2S, HCN. And the Ka values. 6.6 times 10 to the minus 4th, 4.4 times 10 to the minus 7th, 1.1 times 10 to the minus 7th, and 6.2 times 10 to the minus 10th. So you would plug this in. The negative log of 6.6 times 10 to the minus 4th gives us 3.2. That would be the pKa. Pause this video and make sure you can calculate this for the rest of them. Okay, you should have gotten 6.4, 7.0, and 9.2. So which one of these should be the strongest acid? The strongest acid. Right, HF with the lowest pKa is the strongest weak acid, right? These are all weak acids, but this is the strongest of the weak acids. HCN there would then, with the highest pKa, be the weakest. So this is the biggest pKa, but the smallest pKa. So smaller Ka, bigger pKa equals a weaker acid, and a smaller Ka and bigger, a smaller pKa and bigger Ka value is a stronger acid. Okay, I know that this has been a particularly long video. I hope you've hung in there with me. I am going to pick up on the next video with going through the base counterpart of everything we went through today on acids. So if you've understood what we've done on acids, you should be able to pick up on the next part. There will be a follow-up quiz for this video, and I'm going to do the same thing I did with the equilibrium one from last time. It's going to be one problem, and you have to upload your rice table work. So it's going to be a strong acid dissociating problem. I want to see your work. I want to see how you're doing with it, and be able to give you some feedback on if you're not doing it right. So I hope you found that last round was helpful. And when we do this, you can upload as many times as you need to. You can submit as many times as you need to. I will keep giving you feedback until you know you're getting it right. So please go through that process with me. All right, I hope you guys at least enjoyed Thor. I always like when I get to put a picture of Chris Hemsworth in one of my lectures.